Hi, everyone. Thank you for coming back today. And we're really excited to have Dr. Krithika Manohar, who is an assistant professor at mechanical engineering at the University of Washington. She works at the intersection of machine learning, dynamical systems, and control, developing efficient data-driven algorithms for optimal sensor placement, forecasting, and smart manufacturing. She received her PhD in applied mathematics at the University of Washington in 2018, followed by a postdoctoral position and von Karman instructorship at Caltech. Her research leverages dimensionality reduction tools rooted in operator theory and manifold learning to discover physically meaningful features from the data and optimize sensors and actuators for downstream decision-making. Target applications for sparse sensing optimization include fluid flow reconstruction, image recovery, and aircraft manufacturing. She is also interested in sparse sensing and forecasting in the context of partially observed multi-scale systems, which are commonly found in fluid dynamics, material science, and biology. So join me in thanking Dr. Manohar.
Thank you, Peter, for the introduction and kind of outline of the topic. Right, can everyone hear me? Zoom in here. Perfect. Hi, I'm Krithika, and I am in mechanical engineering at University of Washington as an assistant professor there. However, my background, for context, is in computer science and applied math. So I really work on these algorithms and computational methods for control and prediction of large-scale complex systems, such as fluid flows, sensor and actuator placement, digital twins, which are an end-to-end digital representation of a product life cycle or a process, such as an aircraft or a nuclear reactor. Basically, safety critical applications where testing and experiments are dangerous. I also work on characterizing manufacturing processes and the materials involved in these processes. And some collaborators also work on autonomy and control. And I also work on designing optimal actuator placement for control in these large-scale systems. Okay, so here is that promised outline, which Peter kind of already said. So I'm going to discuss algorithms that fit into three buckets, basically. So the first is data-driven modeling. So how do you identify governing models from data when you don't know what they are? These physical processes in engineering are governed by PDEs, ODEs, and SDEs, often all three at different scales of the same system. So one of the techniques we'll use for learning these dynamics, sparse regression or sparse identification of nonlinear dynamics, modal decompositions, and how we leverage the structure we learn from these data-driven models to optimize sensor placements. So this is kind of a design problem on top of an optimization problem, a data-driven optimization problem. And I'll discuss use cases for nuclear digital twins and aircraft manufacturing. I have collaborators at Idaho National Lab and Boeing who work on these. And I'll kind of towards the end talk about moving towards explainability and guarantees for these models, using ideas incorporated from statistical physics, system theory, and operator theory for dynamical systems. Okay, that's kind of a lot. I'm also part of this NSF Center grant, this NSF AI Institute in Dynamic Systems, led by Nathan Kutz and Steve Brunton. This is University of Washington here is the lead institution. We have partnering institutions from across the West Coast and beyond, so Hawaii and Alaska. So these are universities in regions that are geographically isolated from the kind of tech industries that are in Seattle. So we get a lot of collaborations with Amazon, Facebook, because of where we are in Seattle, And we want to extend that reach to the West Coast as well. We also have partners in Harvard and Columbia who co-lead the dynamics and modeling thrust at Columbia, and as well as control thrust. Okay. So research in this area has been interdisciplinary for a lot of reasons. All of those people you saw on the previous slides are, or most of them are in engineering departments. They're also in mathematics and statistics departments. And advancing the fundamental theory and algorithms of AI kind of requires blending approaches from all three perspectives. So dynamics and modeling, control, statistics, as well as optimization. So really 4 approaches. So how many of you are affiliated with engineering, mechanical, aerospace? Oh, okay, perfect. So I don't have to explain all of these to you in detail, but how many of you are in physics, chemistry, biology, biophysics, and neuroscience? Wow, this is probably one of the most diverse audiences that I've spoken to. But basically, this is good because a lot of the researchers and collaborators I work with, around a third of them have a background in physics. Many of them are statisticians. Many of them work in computational neuroscience as well. So a lot of the emerging techniques in physics-informed machine learning and AI have really been driven by advances in these fields and the data collected in these fields. Okay, so maybe I'll start with some of the challenges in dealing with dynamic data, the processes we consider in engineered systems, as well as physical systems. So unlike things like ImageNet and problems in computer vision and natural language processing, we have typically a very small number of samples of dynamic data. Now, each of these samples or snapshots may be high dimensional, but because of the variety of control inputs, parameter regimes, we can only usually get a small number of time-dependent snapshots for these systems. Okay, and second of all, identifying the dynamics that govern these processes directly from data is challenging, but also you have this temporal structure you can leverage. And you can use this to identify nonlinear, chaotic, and even multi-scale dynamics. But a lot of the times these are unknown. So this creates a problem for when you try to design sensors and actuators to either drive or do some sort of feedback control of the system or some sort of high dimensional state estimation. And lastly, a lot of these systems, when you're dealing with real data, are partially observed. So what does that mean? Successive observations are non-Markovian. So this challenges our ability to fit data-driven models. So this kind of partial observation or incorporating memory into the machine learning methods that we use is very important in these data sets. So my perspective is first, we need models of these systems to be able to optimize or design sensors and actuators for feedback control. And this is challenging because although we may have high fidelity data from simulations or CFD or other kind of gray box models, deploying actual sensors is actually very, very expensive. So for example, in an aircraft, you may have only 2 to 4 angle of attack vanes. So this is it. Any additional sensor will cost millions of dollars, and it's just prohibitive. In applications like nuclear reactors, where you're studying the thermal hydraulics of of a heater and the boiling temperatures of the water around this heater, the extreme temperatures and pressures and just the operating conditions inside that heater element make it really difficult to put thermocouples or other ways to actually sense the real-time temperature inside that flow. So this is part of the question that I will try to answer. So let's start with data-driven modeling, and I'll highlight this technique called sparse identification of nonlinear dynamics. You may have heard of it. So this is a way to identify governing equations directly from time trajectories. So the basic idea is you discretize nonlinear terms that you think may drive these equations. A good choice of driving terms would be a library of polynomials with higher and higher order interactions. And then you discretize the time derivative of your inputs. So for this Lorentz model, you have the time derivatives that you're trying to fit in this library of functions, and you impose a sparsity constraint on the identified model so that the model is parsimonious. How many of you have heard of this method? Okay, great. So typically this is solved using some sort of sparse regularization of this least squares problem. So you want to fit or approximate the time derivatives with the matrix library times sparse coefficients. So you're solving for these coefficients and you add a regularizing term that is controlled by the strength lambda. So you can fit this with a lasso regression, or you can do some sort of thresholded least squares algorithm where you repeatedly solve least squares for the coefficients and threshold those smaller coefficients to 0. And this is the latter is often more efficient and easy to implement. Okay, so this was pioneered by Steve Brunton and Nathan Kutz. And one of the challenges in identifying these models is actually the fact that you identify a one parameter family of models that depends on the strength of your sparsity promoting parameter. So along with this, there comes a need for interpreting the solutions of these sparse regression problems that are used to identify the dynamics. How do you know which sparse model optimally describes your system? How do you validate and predict or time step these models that are identified? So as I mentioned, sparse regression identifies one parameter family of models that depends on the sparsity promoting threshold. As you vary this threshold, you identify a different number of terms in the model. And a model selection is driven by the sweet spot between the number of terms identified and the error of the fit of the model. And the way this was done with a lot of the pioneering Cindy work was identifying the Pareto frontier. So achieve the lowest error or generalization error with the minimal number of model terms. And you can see this here for this implicit Cindy model that was published by Neil Mangan. This model is identified by this blue circle here. So this is a different chemotaxis model that's identified, but the same idea applies to other kind of ill-posed problems posed by the sparse regression, where you might have noise in your measurements and you will need to do some sort of search among the identified models to find the one that best describes your data. Now, this is not necessarily a bad thing. You might even find lower order models of things of a chaotic attractor, for example. So one of the main things that my group is working on, one of my postdocs, Andre Clishin, is working on explaining these sparse regression models via the library term interactions. So characterizing the Cindy library, the library matrix, in terms of 1- and 2-term interactions and so on, to basically identify a different type of optimization technique to solve these problems, and also offer a way to interpret the interactions between these terms and how important they are for the trajectory shown here in data, essentially. Yes.
So what if you have like a exponential or sinusoidal independence? Then would this method work or not?
So yes, so if you have exponential or sinusoidal dependence, you can either explicitly include those in the library, or another way those are identified is by their Taylor expansions.
Okay.
So for example, every odd power for one of the sines and every even for one of the cosines, or unless I'm getting that mixed up. Sorry, I'm still getting used to the time difference. Okay. So this brings me to modal decompositions, where how many of you have heard of POD, proper orthogonal decomposition, or dynamic mode decomposition? Great. So these are essentially computational tools that help you learn the structure of dynamic and static data. I think there's a question on Zoom. You can go ahead and ask.
No, I was just saying I have heard of DCA.
Excellent. So the reason I bring up these techniques is how we're going to use them for finding optimal sensor placements. And these low dimensional embeddings are useful for a number of things, including projection-based reduced order models. And they also identify a lower dimensional set of coordinates in terms of these coefficients that help you learn more complex nonlinear embeddings, such as neural networks on this data. So the basic idea is to represent this high dimensional evolution equation or static images by a rank R decomposition in terms of R modes, where R is typically much less than the ambient dimension of the data, and their weighted coefficients AK. So this cylinder flow in the vortex shedding regime is well described by roughly a rank 40 proper orthogonal decomposition. The set of eigenfaces, which are these high resolution images, can be reduced to a linear subspace that is roughly 100 to 150 dimensional. So rather than 1,000 degrees of freedom, you can describe them in terms of the weights of their 100 or so principal components. The temporal structure in your data actually allows much higher compressibility in this representation. But the idea of this slide is that POD modes and principal components and singular value decomposition are all closely related, and in fact, they are equivalent. There are continuous formulations of the proper orthogonal decompositions, which are used for Galerkin projections and things like that, but they can essentially be solved for using the same mathematical tools. This is the foundational idea behind efficient algorithms for optimal sensor placement. This is a really difficult problem, but we can use this dimensionality reduction step in order to optimize sensor placements. Okay, so the POD modes are eigenmodes of the data covariance matrix. There's clarification there, and they are ordered by their energy contribution, which is revealed by the singular value spectrum of the decomposition. So all this requires is taking the SVD of the sequential data, but it doesn't rely on the sequential ordering. And the leading R left singular vectors of the decomposition essentially are your POD modes. And these are the strengths of each mode. So you can see that every successive coefficient is less important than the one before it. And we're going to use this kind of variance characterization property of POD in order to find optimal sensors for control as well as for manufacturing applications. Dynamic mode decomposition are eigenmodes of a linearized flow map that's fit to the data. You can approximate this with just a simple regression on top of an SVD calculation, a reduced SVD calculation. This is really important because this is a 2D flow with roughly 90,000 grid points. So you have a matrix with dimension 90,000 by how many ever snapshots you take. If you have a 3D flow, the curse of dimensionality is going to make the cost of this computation even more inefficient. So if you take, 300 cubed, 300 grid points in each direction, then already you have, millions or billions of grid points. So these linear techniques can actually leverage ideas from randomized linear algebra and compression, matrix compression, in order to efficiently calculate these modal decompositions from a very small number of data samples. This would not be possible with the neural network. We only have 150 snapshots or samples of this flow. The three methods I highlighted are essentially very powerful in the low data, and they can be used to design control laws. That's their real power in engineering systems, as well as help design sensors and actuators to deploy in an actual flow where you can't measure every single grid point in real time. Okay, so this DMD is essentially the spectral stability analysis that you do in a dynamical systems course. It decomposes the flow into these modes that are evolving according to some frequency and some amplitude. So analyzing the result of the DMD regression model actually requires analyzing the spectral content as well as the strength of each mode. Now, there are a number of variants of DMD that are that basically incorporate physical structure or impose some sort of constraint on the identified model. There's optimized DMD, there's physics-informed DMD or PIDMD developed by Peter Ledoux, and there are Python packages that help you compute this more efficiently and more numerically accurate in the presence of noise or other distortions than this exact DMD technique. Okay. Now I will talk about how I use this in my work on data-driven sensing. So the basic idea is data-driven sensing, or the optimization of sensors and actuators to place in the flow, exploits the learned physics from these high-fidelity models. So you can do this by learning coordinates or bases that are relevant to your downstream task, whether that's some sort of parameter estimation, forecasting, or control. And you can use modal decompositions that basically reduce the complexity of the optimization that we'll ultimately do. Okay, so some motivation of why we want to do this for the systems that I highlighted earlier. The choice of measurements or local measurements in real time is crucial for any sort of collective decision making. And we see a number of examples of this in biology, where animals often make on-the-fly decisions without having any global knowledge of the flow around them. They just use localized measurements of the wake structure around them for these swarms of fish. And it's well known that insects have these strain sensors on their wings that are kind of sparsely distributed, that basically enable them to avoid gust disturbances on timescales faster than it takes for their visual processing, for signals to travel to their brain and back. I think this was alluded to in one of yesterday's talks. And this is how, flies avoid when you swat them. It's actually quite remarkable. So we want to leverage these ideas from these, biological inspiration to track select few measurements that are informative of features in the data. And a great use case of this is this manufacturing processes, where we kind of take this idea of sparse sensors on wings and use it to basically reconstruct the structural measurements in the wing-to-body joint on an aircraft. Okay, so this manufacturing applications, let me just kind of set the stage a little bit. So how many of you know what shimming is? So if you ever assembled a piece of furniture, sometimes it needs a little, piece of wood to fill the gaps in between. So I guarantee you everyone has done shimming. So shimming is very important in the Boeing assembly process. What happens is when you have two joining parts, you have to measure the gaps that occur between them and manufacture shims to fit the gaps. So first you need measurements of all these gaps of the two joining, between the two joining surfaces. So historically, this was done in a really manual intensive process where workers would measure the gaps in these confined spaces. First, dry fit the two parts together to measure these gaps, and then disassemble the two parts, so the wing skin and the spars underneath, design the shims and reassemble. So this is in the critical path of assembly. Essentially, the aircraft is built twice. So we want to save this time spent in the critical path. That's the goal here. Because nothing else can be done until the shims are manufactured and the final fit occurs. So predictive shimming is more recently used. So what happens is you have this laser scan system or metrology robot that scans the surface of part A, the joining surface of part A, and the joining surface of part B, generating point clouds of billions of points. And the two surfaces are then computationally processed and then the gaps between the two surfaces are measured. So this is predictive shimming. What we are aiming at is predictive shimming. So instead of following this pipeline where you have this the measurement time required for these robots and the programming time is actually, as well as this processing time, it also adds up. So can we learn patterns from historical shim data or gap data from aircraft that are already built and predictively shim and go directly to this box of shims, basically in seconds on your laptop? So this is one case study, and it turns out, yes, we can. So this was one of my projects. So the data set, we have 10,000 gap measurements of this wing-to-body joint. So this is the wing, and where it joins with the fuselage forms this box-shaped structure. For a 787, this box area is kind of the size of a small studio apartment in Seattle. so you can fit some people in there. So you can imagine the amount of measurement time it takes to scan both surfaces. Again, the magic number is 50. We have 10,000 gap measurements of 50 aircraft that are already sampled. And we want to leverage those to reduce the number of measurements. So we reduce it to a certain amount of target measurements that are informative of these features and actually predict the shim with accuracy that's high enough and comparable to predictive shimming. Okay. And here are the results. So what we did was did a localized robust PCA model. So applied robust PCA to learn the features along each section of the shims. And as it turns out, these wing sections are very closely aligned with the spars or stringers on the wing. And these are our optimized sensor ensembles. And as it turns out, we can predict with up to 99% accuracy the entire gap distribution from these sparse measurements. So we achieved 99% accuracy. That means each of these gap measurements is predicted to within 5,000ths of an inch. That's their manufacturing tolerance, using 30 times fewer measurements. And we achieve accuracy that's comparable to the predictive shimming, which is the current state of the art. So how do we actually do this? So let me go into the methods. Any questions so far?
So how does this model related to dynamic
I will get to that. So we actually use the same sensor optimization methodology to optimize sensors and actuators in a controlled dynamical system. So, so first I'm introducing kind of the computational idea behind optimal sensing using dimensionality reduction.
How different are those two types of wings, and does this generalize?
Which two types of
The 787, 8, and 9.
So it probably won't generalize to new aircraft. So the 787-7 is used for predicting 787-7.
Okay.
So you
kept them both separate.
Yes, exactly. We didn't actually analyze how they would predict with each other, but I think they have a different grid resolution. So you can. Okay, so how do we design sensor measurements? So the problem is to recover a high dimensional state from sparse measurements, where S is our sensing operator that's taking point measurements of this high dimensional signal, where you have ones along this matrix. So this matrix is all zeros and ones. And if X is n dimensional, these are selected rows of the n by n identity. So this corresponds to taking point measurements of the flow and storing it in Y. The reconstruction. So we set up a system of equations to solve for the POD coefficients of your high dimensional state. So we assume that state X is low dimensional in some representation basis. And for now, we're thinking of linear embeddings. Then the reconstruction reduces to estimating these coefficients. So we reduce the dimensionality or the number of degrees of freedom that we need to reconstruct. And this is known as gappy POD reconstruction. It's an old technique used for facial image reconstruction in 1995 by Everson and Surovich. Okay, so you can solve this by solving a least squares problem, essentially. But how do we actually design the sensor matrix? This, depending on how you look at it, is a very difficult optimization problem. If these weights are binary like here, then you have n choose p different possibilities of the sensing matrix. if you look at it as a discrete optimization problem. So P is our sensor budget. So this is already combinatorially exploding complexity. If you have to search over all possible sensing matrices of these size. You can also relax the weights in this matrix to fractional weights and pose this as a convex optimization problem. However, if you do that, then the complexity of solving for these sensors is still cubic in your state dimension and can be really expensive. So we assume the data is low dimensional in this representation basis, and we inject that low dimensional structure into existing systems theoretic or design of experiments objectives. So oftentimes this involves maximizing some measure of the spectrum of this information matrix. This is sometimes known as the Fisher information matrix for this least squares problem. Okay, as it turns out, we can get a very efficient near optimal solution to this problem. This comparable to the convex solvers using just a matrix sub-optimization procedure given by the pivoted QR algorithm. Why does this work? It seems curious that it will work. But essentially, we can also form these optimization problems in terms of minimizing the error covariance volume of the information matrix, or the inverse of the information matrix. So there are different measures of the spectrum we can optimize. One is the determinant, which corresponds to D optimal, which is the product of the eigenvalues of this matrix, or the trace, which is the sum of the eigenvalues of this matrix. These are different scalar measures of the error covariance of your estimate, assuming you have noise on your samples. Okay, so why does this work? The pivoted QR essentially decomposes your linear representation into a unitary R by R matrix, a small square matrix, and a rectangular upper triangular matrix. And at each step, the pivoted QR selects columns or performs a column permutation of this embedding in order to maximize the diagonal entries of R. The determinant the desired determinant we're trying to maximize ends up being the product of the diagonal entries in R. So this is why it works. And at each step, it selects a column index, which corresponds to a spatial location in your flow or your image data set, and pivots it to a leading R by R submatrix with the desired determinant. And the indices are essentially given by this pivoting or permutation operator returned by the QR. We'll actually go through how this works in part 2, but essentially, you can validate the QR optimized placement for a linear state space model. That's very small. So you have 25 states, and you're trying to choose 7 point measurements. That helps optimally reconstruct it in this basis. So what we actually did was search over all the possible placements for this problem. So there's around 500,000 of these. We bin the objective function or its log into a histogram, and we see that the QR optimization is near optimal. The true optimum is here. However, this gap does not affect the reconstruction error much, which is what we'll see in these fluid flow and manufacturing examples. Okay, so this is the manufacturing example you saw earlier. Using the robust PCA model, and the optimization for the sensor ensembles, we were able to reconstruct 99% of the gaps to within manufacturing tolerance. This algorithm was actually deployed into production at Boeing, where it's probably saving them millions of dollars in the critical path. Another aspect of these linear models is that in aircraft, in aerospace industries and the nuclear industries, there are licensing issues when it comes to deploying deep learning models. And I hear this a lot from my collaborators. So for flight control at Boeing, they still use Kalman filters because you can predict the uncertainty or regularize the problem of solving for some gust parameter given sensor measurements. Their state of the art they're working with is Kalman filters. So moving from linear embeddings to nonlinear embeddings requires some sort of explainability, interpretability, and guarantees. And that's something my group is actually working on, and I'll touch on this towards the end. Okay, this just shows the distribution of the error between the optimized samples versus a random placements. So you can see that approximately 98% of the probability mass is below 0.005 of an inch for most of the shims, for all the shims, whereas you only get 50% accuracy with random measurements. Okay, so moving towards explainability and interpretability in engineering systems, we are moving towards digital twins, which are digital representation of a very complex product or process. So for example, in an aircraft, the first digital twin definition came from, I believe, NASA. So it's an integrated multi-physics, multi-scale probabilistic simulation that uses the best available physical models and reduced order models. Sensors are basically the main line of communications between your digital representation and the actual physical product. So the idea of combining reduced order models and learning low dimensional structure from data and using that to optimize sensors that can be deployed on this actual product is actually a very important area of research. And we're currently working on doing that for a nuclear reactor application. So here, the design of sensors, we have constraints that force them to be away from this main heater region, but the heater region has most of the interesting dynamics we wish to capture. We also have constraints on how close these sensors can be. But if these sensors are placed in uninformative locations, then you won't be able to estimate the temperature and pressures accurately. So we need this kind of sensor optimization framework for something like a digital twin of this entire reactor, as well as the heater element that fits into it. Here are the reconstructions for this, for a temperature field for this simulated heater. So we have high fidelity simulations from many different heater powers. And what we're trying to do is actually ensure that the sensors that we place, which will be, thermocouples or other kind of fiber optic sensors, we are able to actually estimate the real-time operating conditions inside an experimental prototype of this. So the heater is electric, and the liquid being heated is actually water. But this is to study the thermal hydraulics of the heated region without actually simulating the neutronics effect, which would be catastrophic. We can see that with the QR optimal sensors, which favors placing sensors really close to the heater region. This is just not feasible in the experimental device. So what we need to do is impose constraints and do a constrained optimization of the same procedure. And we can show that the reconstruction error is still extremely low compared to, random placement or other kind of data agnostic sensor placement techniques. Okay. We can do a similar kind of validation by searching among all allowable placements in our randomized state space model. And we can see that the constrained placements with the dotted line here are actually very close to the optimal placements when you do this discrete optimization. So the red star is the log determinant objective, and the reconstruction error is basically negligible. And you can actually quantify how the reconstruction error will depend on this distance between the objectives. And it's just much smaller than a sensor placement corresponding to this end of the spectrum, which is a random placement. And in one of the constraint cases, we actually identify the true optimum. And because this is a greedy optimization of a submodular design objective, we can actually get very close to the optimum, which is infeasible with other techniques for higher dimensional systems. This would have applications actually to yesterday's talk on the environmental estimation. So when you have really ill-posed problems like groundwater flow, then you want to place sensors at informative features in the simulated model. So there could be a connection there to the sensor placement techniques used in yesterday's talk. Okay, now to your question on how do we use this for dynamic systems? The nuclear system is dynamic as well, but how do you design sparse sensors and actuators for feedback control? So here, this is your dynamical system. I assume this is linear for now. Instead of characterizing the energy spectrum of the dynamics here, we have different observable and controllable spaces. So you may, the control law that drives the system to a stable state may actually have a very low energy contribution that won't be captured by POD. This is well known. What we do instead is a balanced proper orthogonal decomposition that was introduced by Clancy Rowley. So what this does is instead of a set of orthogonal POD modes, you have the direct modes, direct balance modes, and the adjoint balance modes that describe this balanced gradient in the transform coordinates. So essentially, you find a dimensionality reducing transformation in which both the observable and controllable subspaces are the same. Think of it as a generalization of the POD for control systems where you have a control input. A similar idea is, for example, resolvent modeling for fluid flows. So we characterize the observable and controllable subspaces, which we can do from the actual response data. And we can do sensor placement using the same matrix optimization technique on the direct modes and the adjoint modes to optimize the actuator placement. And we actually do this for a linearized Ginsburg-Landau model, which is around 500 grid points for one sensor and actuator to two sensors and actuators. And we actually compare this with an extremely expensive gradient descent techniques that tries to solve the same problem. And what it does is discretize the sensor matrix X, S into from point measurements to Gaussian, to roughly Gaussian measurements centered at where you have the point sensor. So they needed to do this to be able to have a differentiable control objective or sensor placement objective. And what we can see is that our objectives, which are the H2 norms of the resulting control system, a low value is better, are very close to the ones identified by QR and result in the same LQG control gains, and as well as result in very close sensor and actuator placements. So the performance is comparable, whether you decide to use this approach or a much more efficient approach that can scale to 2D and 3D flows that are discretized. And we demonstrate, we validate with the brute force search for the optimum for the 25-state system. This was actually the same, from the same paper shown in one of the previous slides. Okay. I think I'm arriving at the 50-minute mark. So I wanted to talk about some very fresh work that will probably be on archive next week. So one is, this is also work by my postdoc, Andre Cletion, who's working on characterizing the interactions of sparse sensor placements using a statistical physics viewpoint. So basically what this does is rewrite the optimization objective in terms of a Hamiltonian for essentially different, that characterize different sensor placements in terms of one-term interactions, one sensor interactions, plus all two sensor interactions, and actually derive a greedy optimization technique based on minimizing the energy of this interaction. So we actually have some very compelling results on interpreting the sensor placements for the sea surface temperature flow. So this is satellite data, it's actual data. So once you place a sensor, you can get a cost landscape of that describes this objective for where to place the next sensor. And the most informative locations, given you place one sensor, would be these. And you can see they highlight important modes of the climate evolution. This is particularly powerful in the low sensor case. So if you recall, the GAPI formulation assumes you have at least as many measurements as the rank of your model in order to be well posed numerically. But you can actually reduce the number of sensors or measurements you need with the regularizing prior that can also be posed to be data dependent. And what we see is that in the low sensor regimes, where if you have a truncation rank of around 100, which is reasonable for this problem because there's so many complex fluid structures and turbulence, you can actually achieve lower reconstruction error than if you had more sensors than rank of your model. So this is some really cool work, and we're working on casting the sparse regression problems for model identification into a similar framework. Because sparse regression doesn't give you some sort of interpretation of your sparse coefficients identified. It just spits out a sparse coefficient vector. But you can characterize those sparse or those solutions in terms of, degree 1 polynomials in your library, or two-term interactions between those monomials in your SIMD library, for example. So this is very fresh work, and this is something we're working on extending to sparse regression. Okay. You can see similar, essentially, number of sensor studies. So you're increasing the number of sensors and you're studying the error. And we see the same thing for especially the physics dominated flow, that the optimization posed in terms of the 2-point interactions, that greedy optimization on the earlier slide, actually achieves lower error in these data sets with physical and dynamic structure than the plain QR. pivoting procedure with gapping POD. This preprint will be up on archive roughly next week, so you can look at this in some more detail. I don't think I have time to cover everything, but I also want to mention a new deep learning based sensing paradigm. So this idea basically incorporates temporal structure into a shallow decoder network in order to predict or reconstruct a very high dimensional turbulent fluid flow from very sparse measurements in the sequential data. So this actually leverages sequential information because of the long short-term cells in this network. So combining a recurrent architecture with a decoder architecture to basically compress the dimensionality here, but also incorporate the time embedding of these measurements. When you do this, it turns out that the reconstruction quality does not depend as much on your actual sensors that are selected. And that's because in this 2D flows, most measurements are informative of this turbulent structure. But when you use the QR gappy sensors, it ensures that you basically place sensors at informative locations along the flow. And the reconstruction error quality is much higher than with the linear embedding reconstruction. So this allows minimal sensing. So 3 sensors in a turbulent flows incorporating time history. It enables random placement, even data anomaly placements, or at least for higher dimensional flows, you want to make sure that your sensors are placed somewhere informative and not in a dead spot. And we're working, one of my students, Jan Williams, is working on embedding this framework with model predictive control using echo state networks, rather than this recurrent neural network architecture here. And that saves you the computational complexity of doing backpropagation. Echo state networks are similar in flavor to an RNN, but they don't require backpropagation to optimize. They use some fixed inputs determined by random initializations. And the key idea there that enables prediction and forecasting of these fluid flows and climate systems is lifting to a random reservoir state that is governed by its own dynamics. If you're interested in that, we can talk offline as well. There's a lot of interesting directions in that in this work. Okay, I think this idea actually corresponds to how to design neural network architectures and inform them using system identification techniques. So when you do linear system identification, you actually construct this Hankel matrix of delay embedded samples into a snapshot matrix. This is, I'll just call this the Hankel delay matrix. And this actually corresponds to something we know as the Koopman operator acting on successive samples of this dynamic system. So this has very rich connections to operator and systems theory, and we're basically embedding the structure into a neural network. And similar ideas have been done to, discover nonlinear embeddings for Koopman eigenfunctions. So DMD goes toward identifying the spectrum of this infinite dimensional Koopman operator. And there's a tremendous amount of work on doing that and how it helps forecast and control high dimensional fluid flows and other systems. Okay, I think I'll stop here and leave some time for questions and get to my other slides in part 2 maybe.
So you, so you talked about utilizing the fact that it's time ordered either with recurring networks or with like DMD. What are good things to keep in mind when, say, you have a lot of data of like one that you might learn some type of periodicity for like this specific time ordered stuff, but you want to be able to generalize it to a different case. So like, for instance, with the planes, maybe they're flying this specific route, but you want to be able to use other routes or something. You want to be able to generalize to that.
Yeah, so I guess how do you generalize to different parameter regimes for these time-dependent techniques? So DMD and POD to some extent, there are parameter-dependent reduced order models that have had a lot of success with that. So basically, create a separate linear model, POD or DMD, for the different parameter regimes that you sampled, and use the low dimensional structure to interpolate between where you haven't sampled. So there's a large literature on parametric reduced order models that help you do this. And that's one of the benefits of the dimensionality reduction approach. So instead of interpolating in a 90,000 dimensional space, you're basically you can even learn nonlinear embeddings that connect the lower order models. And it's used a lot for circuit modeling and also learning, discovering bifurcation structures or reduced order models that describe evolution of PDs, reduced order ODE models that describe models of PDs.
For your Hamiltonian model, why do you think the error function is not monotonic with respect to the number of sensors?
Okay, so very astute observation. So when P is equal to R, when the number of sensors is equal to the rank of your model, you're solving a linear, you're just doing a linear solution. Solving a square system of matrices of equations is ill-conditioned, more ill-conditioned than adding a measurement or moving a measurement with and adding a prior for numerical reasons. I'll show you an example of this, but basically, if you think of doing polynomial interpolation, where you're enforcing your interpolant to exactly interpolate your points in a function, that results in what's known as the Runge phenomenon. You have these oscillations that contribute to error, and that's because of the equality constraint. When you're solving an overdetermined system of equations, you're basically finding the closest solution to the range of your linear operator, instead of enforcing that forcing your interpolant to go through those points. So instead, when you do polynomial regression, you just find the polynomial of best fit. That may not actually go through all the points. So when you have noisy data, that may be the thing to do. There is an example I'll probably go through in part 2.